Welcome to the Andreas Orthey podcast series on robotics. My name is Andreas Orthey and my first guest is James Kuffner. James is really one of the most successful roboticists worldwide. He's on the board of directors at Toyota Motor Corporation and he was co-founder of the Toyota Research Institute and CEO and co-founder of Woven City, an ambitious project by Toyota to build a novel type of city in Shizuoka Prefecture in Japan. James was also influential in the Google self-driving car project, which later became Waymo, one of the leading companies on self-driving technologies. James not only holds a PhD from Stanford University, but he also made substantial contributions to robot motion planning, and he ran a very successful research lab as professor at Carnegie Mellon University. I met James at a big robotics conference in Rotterdam in the Netherlands. When I asked him if he wanted to do a podcast with me, he immediately said, well, yes, of course, let's do it. It turns out James did not only have a stellar career, but he's also a great human being who cares deeply about the world we live in. I hope you enjoy my conversation with James as much as I did. Without further ado, here's James Kuffner. Thank you so much and welcome, James.
Yeah, thank you very much for inviting me.
Yeah, it's my absolute pleasure to have you here and thank you so much for taking some time out of your busy schedule. I think you were involved in so many different projects and I want to basically talk about almost all of them. But before we go there, I just wanted to maybe take a little bit of time to talk a bit about your background, to understand where you come from. Where were you actually born and how was life growing up for you?
I was born in New York, but very soon moved to Portland, Oregon, and I grew up in Oregon and went to the university in California, Stanford University. Was there for 10 years. During that time, I was studying computer science. I also spent half a year in Oxford, where I studied astrophysics.
Oh, nice.
But became very fascinated by robotics, and that had been a huge motivation for me. I went to the University of Tokyo. At the time, I was...
Can I just interject? Sure. How did you actually get into robotics in the first place? So, I mean, can you actually trace this somehow back and tell me, there was this one moment where you suddenly felt this urge to pursue robotics?
Thank you. So, I think like many robotics professionals, they fell in love when they were young. Mm-hmm. So for me, I saw Star Wars and movies that presented intelligent machines. And at the time, I was able to get my first computer, which was a TRS-80 Radio Shack computer that had 4 kilobytes of RAM.
Nice.
And basically taught myself how to program with some friends who are also dabbling. Just the fact that a computer could be programmed and you could make it do interesting things. I mostly made games when I was a kid, but
I think that's quite common. So I think a lot of people in software development and robotics, they just started programming games, and this is how they actually ended up here.
Yeah, and in many ways, to make a game interesting, there's non-player characters that have some agency or have some behaviors, and in the early primitive games, the behaviors are not so sophisticated, but now, of course, in modern games, you're basically building virtual robots with behaviors and actions that are very complex and dialogue. And so, in many ways, I guess embodying these agents into a machine that can actually change the world became something really fascinating for me. And in the mid-90s, about 80 to 85% of the world's robots were in Japan, and that motivated me to learn Japanese. And when I saw Honda's walking robots, the P2, and then later Asimo, I really felt like I had to be part of this humanoid robot. It was reminding me of C-3PO and the many intelligent robots that inspired us.
So how old were you actually when you first started to get into programming?
about 10 years old or 12 years
wow.
old. Probably about 12 years old.
So that is when you got your first computer.
That's right. It was 1983, I think.
Nice.
Yeah.
And so what kind of programming language was
it was
in use
assembly,
there?
but also basic. And yeah, I had stored all my computer programs on a cassette tape. That was quite slow, but it was the same kind of tape that was playing music at the time. And then later, the next generation of computer I programmed was an Apple II, and that had a floppy disk drive, the 5 1/4 inch ones, and so I was storing all my games on there.
Well, then it's not surprising that you actually got into computer science. So how did it actually happen that you ended up in Stanford University for your computer science degree? How hard was it actually at this time to get into Stanford, and what were the challenges there?
Yeah, no, I was very fortunate. I had been studying pretty hard, was very interested in mathematics and science from a young age, and I got a math award from Oregon, but I was very interested in developing skills in computers, or using computers to do something interesting. And I was fortunate to be accepted at Stanford, and it was a wonderful place to learn. It was a place where you meet a lot of other interesting people who are very diverse from all over the world. One thing I loved about being at a university that was embedded in Silicon Valley was there was a strong connection with companies that were being created. And in the 90s, of course, the internet was just coming online, and suddenly we could communicate from anyone around the world, and new companies were being born, and it was a really exciting time to study and be at Stanford. And over half the people in Silicon Valley were not born in the U.S. They were coming from different countries, and I just loved interacting and learning from those people.
And so while you were at Stanford, at some point you got super fascinated by the robotics research field. And so how did this actually happen? Was it a specific course or a specific teacher who inspired you to go into this area and actually do a PhD in robotics?
I had been taking computer graphics. I was still very much interested in games, and what was happening at the time was the industry, which had hand animated 3D graphics, especially for character motion, was now turning towards technology, computer vision for optical motion capture. And in the mid-90s, I created a startup company called the Motion Factory with some of my colleagues, and we were basically providing tools for generating motion inside games for human characters or complex articulated characters, mostly human characters. And we created middleware for games. One of the games that it was used for was Prince of Persia 3D to do the animation. But it just meant that you didn't have to hire a talented animator to hand animate all the joints for someone walking or running or jumping. You could just affix optical motion markers onto the body of a person, have them do a performance, and then triangulate and track those points using cameras, and then recreate the jointed motion so that suddenly you had very realistic looking motions that captured the dynamics of the body and the expressiveness. And now, of course, that's very common to have in movies and games, to have optical motion capture or other types of motion capture, but at the time it was quite new. And stitching it together so that it was continuous and planned. So we were doing motion planning technology for characters, like human characters.
And this was still when you were at Stanford,
yes.
Right?
And eventually our company was bought by Avid, and so that was a very interesting experience for me to learn about how companies are formed and how you can have an idea and license technology. But I decided to go back to school, and I really wanted to finish my PhD, I came from a family of teachers, and that was something that I really wanted to do, very passionate about education. So I went back and eventually got my PhD, but during the time I was taking robotics classes because a lot of the mathematics you need for doing 3D character animation is really fundamental to how you control robots. Spatial math and geometry and the dynamics, understanding the physics of motion really led me to be excited about how now 3D graphics cards were just invented. We were having 3D games, and virtual reality was starting to become something that's possible. So many people were imagining how we could recreate the three-dimensional world virtually. And then what we realized is that in order to have advances in computer vision, you could create synthetic data now. And so, Carlo Tomasi, who was teaching vision at the time, had a wonderful phrase where he was saying that, computer graphics is the inverse of vision. And I was really interested in computer graphics. I was taking Mark Lavoie's class at Stanford, and it was a model to create an image. And we were trying to make it very realistic with ray tracing or other technology for realistic graphics. But then vision basically being you have an image, and now you're trying to infer the model. So an inverse operation, and I found that fascinating, and something that robots needed to do in order to do something interesting is how do they take a perception of the world, create a model, and then do something interesting. So programming a non-player character in a game, but now embedding that decision making into a physical system became so fascinating. And when I saw the video of the walking humanoids from Japan, I said, this is something I have to do. So I joined the Stanford Robotics Lab, and I took a motion planning class from Professor Jean-Claude Latombe, and joined his lab as a PhD student.
So how did it actually happen that you switched from computer vision to motion planning? Because a lot of your research later on was on motion planning actually, and not on computer vision where you actually started in. So how did this actually happen?
So I was taking vision and graphics and control and physics and all of the things that you need. I mean, one of the things that's really interesting about studying robotics is that it is so interdisciplinary. You need to, if you want to build a robot, you have to understand power electronics and mechatronics and mechanical engineering and
you need to
controls and design, and then you have a human interface and interaction. So it's a very interdisciplinary, and at the time, Stanford didn't have a robotics PhD. Later, when I joined Carnegie Mellon as a professor, I joined the Robotics Institute where they teach robotics. And so we, that curriculum was customized to be interdisciplinary. But people who were studying robotics at Stanford, they either were part of the aeronautics, astronautics lab, or they were part of the computer science robotics lab, or there was another mechanical engineering robotics lab. And so depending on your specialty, you had a different flavor of robotics you were working on. Since I was a computer scientist, I was really thinking about algorithms and how do we process data and embed intelligence or decision making and planning into a robot. So really, that was something that I was working on a lot, and at the same time trying to pick up as much as I could about mechanical design and electronics and control.
Talking about motion planning, I think one of the great contributions also from you is this one algorithm, RRT, rapidly exploring random trees, which is basically really one of the algorithms at the very foundation of robotics. So can you tell me a little bit about the background story of RRT? How did it actually come to the creation of RRT, and what was the development like?
Yeah, it was, there's some times in your life where you are very fortunate, and in my case, I had been very lucky to be working at Jean-Claude's lab at a time when Steve Laval, who graduated from Illinois under Seth Hutchinson, had joined as a postdoc. And he was trained in electrical engineering and had a very good controls and math background. and I was doing a lot of software engineering. We just formed a really good partnership, and I learned so much from him. And so we started collaborating, and at the time, motion planning in the 80s had been a lot about theory and geometric techniques. So really hard analytical geometry to have provability about finding paths and feasibility and configuration space formulations. But the problem was many of these techniques didn't scale to the practical problems that we wanted to solve. If you were thinking about a 6-dimensional configuration space for a robot arm or a 30-dimensional space for a humanoid, these techniques didn't scale. But new techniques, Barracond and Latom's paper on randomized planning really broke a mold and opened up a lot of new ideas. Is that say, well, we don't have to have an exhaustive optimal plan like A* that discretizes the entire space and you have to store it all in memory. Instead, you could sample. You could sample the space, and you could sample it randomly, or you could do gradient descent. And of course, the Barracond and Latome planner was doing random walks and then gradient descent. And Steve had been thinking about there must be a better way to explore a space and not get trapped in local minima, and have an algorithm that would be able to sample quickly and efficiently, but at the same time converge towards exploring all the space. Mm-hmm. And so that became like this quest, and he had developed a sampling method that became the RRT sampling method, but there was no planner that yet, an algorithm that you could actually run to find paths. And so we had this great collaboration, and it became a chapter of my thesis, is developing the RRT-Connect algorithm. So you have the RRT sampling the space, but growing 2 trees, one from the start, one from the goal. They try to grow the trees toward each other. So the Connect heuristic provides a greedy, essentially a gradient descent function that allows you to quickly traverse large parts of open space, but at the same time, will not get stuck because it's biased to large Voronoi regions of unexplored space, and in the limit approaches the sampling distribution, which is what you want. So I felt we were really lucky that we had this great collaboration. I implemented some software that still works, and we were able to, I think because it was simple, also to implement, and just a half a page of pseudocode, you could implement this powerful planner. Many people used it, and I was very honored that this is still being used today as a benchmark after 25 years of when we developed it.
Yeah, that's a good point. So I think there are so many algorithms developed, and a lot of people are really excited about something, and then 2 years later it's forgotten. But with RRT, it's really not the case at all. So I think there's still research going on. People in industry are using it. So what do you think are like the main factors of why there's such a long-term success of RRT?
Yeah, I do think the simplicity of implementing it has helped adoption. We also published some versions of the code, and other people have published versions of the code that were quickly adopted, and we were very surprised that many people used it and were solving lots of problems, but they also were improving. They were adding techniques, improving heuristics. One of the things I think that is nice about it is it separates the sampling function and it separates the heuristics into things that you can tune independently of the algorithm itself. And you can also have a single tree, or you can have a bidirectional tree, or you can have a very well-informed heuristic, or more of a blind heuristic, or no heuristic at all, and just do a uniform sampling. You can do importance sampling, you can do deterministic sampling. So many people were bringing different improvements that fit the applications and got better performance. And so because it was easy to do that, you didn't have to rewrite the whole algorithm, you could just replace one function or replace one component. I think it led to a lot of use, and now there's hundreds and hundreds of variants that are solving different problems. But that was a complete surprise to us, to be honest.
Yeah, I think so. So you would say basically flexibility and modularity are the main factors of the success.
Yeah, I do think the other thing that was beneficial was that it, as a baseline, the baseline algorithm performed quite well across a large diversity of problems with a large diversity of configuration space situations. That's hard to do. It's hard to get an algorithm that performs on average very well over a large diversity of situations, and we were lucky that the algorithm seems to be quite robust to those kinds of variances.
There's still research going on RRT right now. Do you actually think there's still value in research in motion planning, or do you think this is actually a topic which is completely solved by RRT and there's no research needed anymore?
Oh no, I mean, there's still so many things that can be done, which is exciting. And there was a joke actually that we used to tell our incoming PhD students at Carnegie Mellon when they were trying to decide what to study in computer science, because there were three types of people. There were people who would come in thinking they're going to do hardware or systems, and then there were people who came in thinking that they were going to do algorithms and language, and then there were people who came in thinking they were going to do theory, and basically, like in life, when you start out as kind of a left-wing person, you get more conservative as a right-wing person. So a left-wing roboticist who's coming in doing theory, usually by the time they graduated, they did something in algorithms. And someone coming in thinking they're going to do algorithms, maybe they would finish their thesis with a systems degree, and someone coming in thinking they're doing systems, they usually would drop out of the program and start a company because they're doing something practical. But in my case, I think the algorithms improvements that we were seeing and the variations that we were seeing, I think there's still so many unsolved problems in planning motion. Biological systems, humans, animals are so amazing at control and effortlessly can navigate and pick things up with complicated constraints and force control and collision spaces and obstacles, and that's something our robots still do not have the full capabilities. But the joke was that if you did a thesis in algorithms, you could republish that thesis 10 years later as real time. Just because Moore's law would help you.
True. Speaking of Moore's law, so today we are really living in the area of big data, large language models. So some people actually believe that they will solve everything. Maybe motion planning will be deprecated. What are your thoughts on that? So will RT stop being useful at some point and we just can rely on a large language model?
I am not sure, to be honest, but I have my doubt that planning in general will never more be needed. And I mentioned a little bit in my keynote here, but I've been thinking deeply about intelligence. Like, people are using the term AI a lot more now. But what does it actually mean, and what actually does big data provide to robots? And that's why I've been promoting this notion that, to me, intelligence, logic, reasoning, and applying that to solve problems in a novel way, and not just imitating past data, coming up with something new. It's about search. And computers are really good at search and building algorithms that are either searching configuration spaces in the case of motion planning, or they're searching task sequences, or they're searching possible actions to take. These are things that I think are fundamental to having an embodied intelligence, really doing logic and reasoning about the consequences of the actions. And instead, when you're embedding a robot with lots of data of let's say, previous tasks that have been performed this way, either captured from a human, like in supervised learning, or another robot, or generated synthetically. In each of those cases, what you're actually providing the robot with is experience. And there's a difference between intelligence and experience. And in English, we ascribe intelligence a little bit differently than what we describe someone who has a lot of life experience. And to me, that's wisdom. And so I've been promoting this idea of actually what machine learning and data sets are providing to robots is artificial experience, not necessarily artificial intelligence. And a lot of people misunderstand a program like AlphaGo, where they think it's just learning or a neural net, but it's actually a search algorithm that's deciding the move. It's a Monte Carlo search tree, a randomized a technique, but then what's learned is the heuristic, and that heuristic is trained from experience gained by thousands and thousands of previous games of Go from human players, but also in the AlphaZero case, it's played against itself and created millions of years of experience of playing many, many different Go games, and using that to train. So it has both the wisdom and the intelligence to be a skillful player. And I think in many domains that'll be true. So we still need the intelligence, we still need search, we still need decision making and exploring action spaces, but at the same time we also need experience and wisdom. And so artificial experience and artificial intelligence are how we create useful robots. That's what I hope.
Okay, that sounds pretty good. So how long do you think it will take to have like a really intelligent robot running around here and doing tasks very similar to what humans can do? So how long, what kind of time horizon, if that is even possible in your opinion?
It is so hard and so dangerous to make a time prediction, but I am very optimistic that in my lifetime, hopefully, I'm 53 now, but if I can live another 50 years, I hope that we will see lots of incredible intelligent machines helping us live better lives. And I hope that as a species and as a planet, we will leverage that technology to support healthy human life. That's one of the things that we should never forget is the goal. And my friend Dr. Gil Pratt, who I've collaborated with a lot, we co-founded the Toyota Research Institute together. He had explained to me that before AI, in the field, there was IA, which is intelligence amplification. So people firmly thought that computers were amplifying human intelligence as opposed to replacing humans. And I actually like that. Like, can we build robots that amplify human experience and skill? And in many ways, that's what the machines that we're building are doing. They're helping us, like in a car, move further and faster than our biological limits. And now we have thinking machines that help us process data and do calculations beyond the capabilities of our own brains. And I hope that continues.
So to actually achieve like some really intelligent robot, do you think we have already all the tools? Or do you think there need to be like another breakthrough happening before we can actually get to like some kind of really human level intelligent machine?
That's a really hard problem to answer, but precisely. But yeah, I would say it really depends on the goal of the machine. Like what is it for? And there's been some bifurcation in the field about building special purpose machines that do one task really well, whether it's playing chess or playing Go or assembling a robot or assembling a car or welding pieces of metal together. Those are really specialized tasks, and we have expert systems that are doing those specialized tasks now better than humans can do. But many people are saying, well, what we really want to build is an artificial general intelligence, something that can do anything expertly and learn new tasks efficiently. Those are something that I think we still maybe don't have all the pieces, but we're getting closer to demonstrating more and more of those capabilities with the contexts of large language models, large data sets. I think one of the things that's exciting to me, at least to help accelerate robotics, is it's actually back to graphics. We now have graphics technology that can create virtual sensors, and cameras are one of the key sensors that humans use, and animals use. The visual sensor, informs so much of the behavior and action making. Now we have robots that can see, and the computer vision's getting better. But in order to virtualize that experience and train, we need photorealistic rendering, we need graphics, and now photorealistic rendering is getting almost indistinguishable from photos and images of the real world. So we can virtualize the sensory experience of a robot, embed a robot in a virtual world where it can learn and improve its behavior, and create a lot of large synthetic data sets that I think could be used to make the robot systems smarter and more capable in the real world, which is really exciting to me. So people have talked about robot dreams, and I've always thought that it shouldn't be just dreaming, because dreaming, you imagine a more haphazard, kind of random exploration of consciousness when you dream. But I think a robot should meditate, meaning we actually built a program that does grasp exploration. So it's searching for grasp, like how to pick up this object many different ways, and analyzing force closure and applying perturbations and noise to find stable grasp of any object. And it takes a long time, but because we have cloud computing, we can run this, and it can run in parallel and randomly try many different types of grasps. But after the program finishes, it has an optimized list of the most stable approaches to grasp an object. And to me, that's like a robot closing its eyes, meditating on an object, and then waking up enlightened and saying, now I know how to grasp this object. And what's beautiful is that skill and knowledge can be stored and transferred and then communicated instantly to any other robot. So that to me has been why I've been in the last 10 years or more so excited about cloud robotics. The ability to leverage cloud computing and fleet intelligence, fleet learning, that we can use to improve the intelligence of robots and robots' experiences, collecting that artificial experience, and then sharing that knowledge so that all the robots become smarter.
Yeah, cloud robotics is a very good topic, which I wanted to talk to you about. So one thing which I believe is like very, very crucial there, for example, if you have a robot which is really working in a safety critical environment and where latency is like a big issue. So how can we actually make sure that the robot meditates but not for too long, so that for example, I don't know, the car is driving and then suddenly a child is on the street, what are you doing? You can't meditate for like minutes or something. You need like a decision right now. So how do you actually make this trade-off between like meditating versus doing some decision right now?
Yeah, no, that's a very good point. And, we should distinguish between the training or the studying and the learning phase of a program, and then the execution. So clearly, when a robot is making a decision in an environment where you have real-time constraints, that means you cannot have an unbounded execution program running. It has to, within a certain number of milliseconds, output a command. That's of course the case for automated driving. That's the case for robots, that have functional safety requirements. So we definitely need to have a program that can execute and safe and reason about the bounds of its behavior and keep itself safe, and have proper redundancy during the execution phase. But when we're thinking about training, that could be something that's offline. It runs in the cloud, it doesn't run on the robot, and that's how we're actually building neural networks today. So a cloud trains a neural network, but then the parameters of that neural network and the code that actually evaluates the network can be embedded in a device and on your phone or on a robot, and it's independent of the learning phase. So for me, a robot dreaming about how to grasp an object can be done offline without any real-time constraint, but then the knowledge of how to grasp is then given to a robot that is embedded, and it can utilize that instantly in a real-time control loop and maintain safety.
So I just wanted to talk a little bit about your time after you did your PhD at Stanford. So you got actually a research grant from the Japanese Foundation of Science.
Yes.
And you were able to actually move for 2 years for postdoc phase to Japan. So how did you actually become fascinated with Japan in the first place?
Well, I saw the walking robots, and I said I really have to
be in
go
Japan
there
at
and
least
learn
once.
and learn from, and people had told me that if you really want to, my weakness was actually mechatronics, mechanical engineering, electrical engineering. I felt like I had a pretty good handle on computer science. I'd taken computer science for many years at Stanford, and I understood software engineering. But I wanted to learn more about mechanical systems and building them and programming them. And so I studied Japanese for 2 years, and I went to Jean-Claude Latome, my advisor, and I asked him, I said, who should I study with? And he gave me 2 names, Professor Hirose from the Tokyo Institute of Technology, who I was able to do my first summer internship with in 1995 as part of the National Science Foundation summer internship. And I learned so much from his lab. I got really inspired and just fell in love with the people and the country and the technology and the culture and the language. And I was motivated even more. And the second name he gave me was Professor Inoue, who was running the Joho System Kogakubu Laboratory, the JSK lab at the University of Tokyo, which was really combining a lot about computer science. They had actually been programming their mechanical systems with Lisp. So they were using advanced kind of AI languages, functional languages, even though they were doing a lot of mechanical system and mechanical engineering. So that was a really good combination of computer science and mechatronics and electronics. And so I joined that laboratory, and the JSPS, the Japan Society for the Promotion of Science, which is Gakujitsu Shinkokai. I was a Tokubetsu Kenkyuin, which was the special researcher.
And so what is your opinion of about the technological level of Japan? So I heard already both versions. So some people say, okay, Japan is so far ahead in terms of robotics, for example. And then I heard also from some people, no, that's not the case at all. They are so far behind actually in software development and robotics. So what do you actually think? Did this actually change over time? And what is your current opinion on that?
So I definitely think that in the mid-'80s, the level of technology for robotics was the best in the world. Most of the robots were in Japan. They were helping build cars and manufacture personal electronics and doing lots of different things. And still we have some incredible robotic innovation in Japan, mechatronic innovation. But I think they have fallen behind in software, which has become an increasingly important part of what we expect of a robot. And there's lots of different reasons for that, but I do think that one of the things that's wonderful about working in Japan, and I've been working there for the past 6 years as part of Toyota, learning how to build vehicles and program to be intelligent vehicles. But they have a concept of monozukuri in Japanese, which essentially is craftsmanship. And making things, the art and science and the craftsmanship of making things, the attention to detail, and this cultural tradition of people adopting a trade and trying to become an expert. And they say you should spend 10,000 hours at something in order to master it.
Yeah.
And so there's this really deep, appreciation and respect for people that make things. And I hope Japan never loses that, because they still continue to make some of the world's best things, whether it's lenses. Some of the best lenses for cameras are all made in Japan. Made in Japan symbolizes quality, craftsmanship. And so that is something that they need. But I do think that improving software education, increasing the talent in software is something that needs to happen in Japan. Otherwise, they will fall behind. And now I think most of the world's robots are in China.
Mm-hmm. And do you think the work mentality in Japan is better, or I don't know, compared to the US? So do you think this whole concept of mastery is more embedded into the mind of the Japanese people?
I could do a whole other podcast about that, but I do think that obviously there is a workaholic culture in Japan. People have a lot of their self-worth and societal worth tied to their job and their profession, which can be good and bad. There's pros and cons to everything, but sometimes at the neglect of families, and of course they're having a population crisis now. People are choosing not to have children, so their population's actually shrinking, and it's happening in other parts of the world as well. But there's a lot of unhappiness if you don't have work-life balance. So that's something that I think is true. I think for the U.S., obviously, because there's so many different kinds of people, and there's so many people who didn't grow up in the U.S. who come and work there. It really depends on the person. But one of the things I do value about having spent 20 years of my life in Silicon Valley, because after Carnegie Mellon I went and joined Google, I really respect the openness to try new things and not be afraid to fail. In Silicon Valley, if somebody had started 2 or 3 companies and failed, you would want to hire that person because you'd be like, hey, that person has experience and knowledge and maybe can help me avoid the same mistakes. But in Japan and some other Asian societies, it's changing, but there's still a little bit of a feeling that if you fail, that you take it really personally and people will label you as a failure, not that your idea was a failure. And so because people embody that a lot, and actually they hadn't changed the corporate veil laws for a long time, so if you were an entrepreneur and you started a company in Japan, investors could actually sue you if the company failed for your own personal assets. And so there was a real hesitation, and that's why there are so few startups in Japan until recently, where compared to the population there should be many, many more and much more innovation. So I think Japan has to embrace failure and learn from failure, and that's something that's actually part of Toyota's philosophy. Kiichiro Toyota had always promoted that we should learn from failure. There is no failure if you're learning. So that's something that I think I value much about the Silicon Valley mentality. There's lots of ideas that fail, but the ones that succeed tend to be big.
Yeah. And do you think this is already embedded into the mind of people at Toyota, or do you think this is also something which is slowly I don't know, percolating into the mind of Japanese people?
I think it really depends on the person, especially if people have lived abroad, or they've worked in different companies, or they've had a diverse experience, or they've tried things or started companies. So I've met some amazing entrepreneurs in Japan who are so creative and bold, and I do think that there are some people who are very rigid and have a more fixed mindset, and of course these people exist everywhere, in every country, but maybe in Japan I think it's changing for the better and it's moving in the right direction, but I would say still maybe behind some other countries.
Yeah, that's
you think about a country like Israel, which has incredible amounts of startups for the size of the country itself. That's incredible.
Yeah, for sure. So let's move back a little bit to the US again. So after you actually completed your stay in Japan, you became assistant professor at Carnegie Mellon, right?
Yes.
Can you tell me a little bit about how you actually ended up at Carnegie Mellon and what was it like to start your own labs there?
I had applied for faculty jobs, and I really did want to learn and teach robotics. And the Robotics Institute was a dream job for me. Carnegie Mellon was the first PhD program in robotics in the world. And Takeo Kanade, who was the director at the time, I had really respected, and he had been teaching, along with Carlo Tomasi, computer vision techniques that I really felt were going to help me as a motion planning researcher. Mm-hmm. So one thing I learned after trying to put planning algorithms in so many robots was it didn't matter if I had the world's best motion planner. If the robot perception didn't work, mm-hmm. it meant that the robot's model of the world was wrong, and therefore the plan that I was making was pretty much useless. Mm-hmm. So I felt we actually have to fix this problem at the source, which is how can we make sure that the robot's model of the world is at least good enough so that the plan and the reasoning about the world and the actions mm-hmm. Is going to be useful and help the robot achieve its goal. So I wanted to partner with people who were doing, vision and perception and building systems. And the Robotics Institute was such a dream come true for me to be a professor there and teach. And one of the first things I did actually was I created Carnegie Mellon's first video game programming class.
That sounds very good to get people interested, yeah, for sure.
Yeah.
So what would you say were like your biggest, most successful collaborations while you were at Carnegie Mellon in your lab?
I was very lucky to have a mentor, Jessica Hodgins, who was a leader there and had done some amazing work with Mark Raybert and at MIT and other faculty. She was also doing graphics, so she really understood well what I felt was the connection between computer graphics and modeling and making robots smarter and reasoning about dynamics and physics of motion. And so I learned so much from her. She helped me a lot and established great collaborations from the beginning with her students and her lab postdocs. Nancy Pollard, Chris Atkinson, who was doing learning, and that was my real first exposure to robot learning was through Chris Atkinson, and he was amazing to work with because he would always get to the heart of what were some of the weaknesses in the system, mm-hmm. And that really helped me a lot. So I had wonderful collaborations with so many wonderful faculty at Carnegie Mellon. And I just really loved working there.
And then at some point you also became a member of Google. So how did this actually happen, and so what was your role in the beginning there?
Yeah, so I had been helping support Carnegie Mellon's entries into the DARPA challenge and the Urban Challenge through motion planning students. One was Dave Ferguson, who had worked on the parking lot planner and the motion planning for the Urban Challenge car, and interacting with lots of students who were working on that. I didn't have students directly working on the team, but I really was amazed that after such a short amount of time, so much progress could be made. And for those who were not familiar, the U.S. government had been trying to fund intelligent vehicles for a long time, and Carnegie Mellon had been building things like NavLab and making a lot of progress, but it was costing a lot of money because it is expensive to develop these things, and you have LiDARs and expensive sensors mm-hmm. and GPS that didn't quite work yet. So you had all these things, but then DARPA did this really clever thing, which is, okay, well, instead of just giving tens of millions of dollars to these teams, we're just going to invite people to compete, and we'll have $1 million prize, and we say, okay, whoever does the best mm-hmm. will win the prize. And then suddenly all this other funding mm-hmm. from other sources was coming in and applied to the problem, and they made a lot of progress. And the first time they didn't make the 179-mile challenge. I think that it was 179. The best team was Carnegie Mellon. It went like 17 miles. And then, like the next year, 4 teams actually completed the entire race, and that was amazing. Yeah, it was incredible excitement. And what happened is that after the Urban Challenge, Sebastian Thrun, who had been at Carnegie Mellon and worked with the team, had brought his students to Stanford, and then Stanford had won the DARPA Challenge, and then 2 years later, CMU team won the Urban Challenge. So between those 2 teams, Google had decided that they would say, can we commercialize this technology? They kind of saw that if we embed some of the latest technology into cars, that it would be a huge business model and disrupt transportation for the better. So they were gathering a small group of people, experts from Carnegie Mellon and Stanford and other places to form a team that would just try. And we were given a crazy challenge, within 2 years, can you drive 1,000 miles autonomously? That was called the Larry 1K Challenge. And there were 12 of us in those days. And I heard about it, and I decided that I had to be a part of it. It was too exciting to pass up, even though I never thought that I would give up my tenure job at Carnegie Mellon. And I knew it was going to take longer than a year. I couldn't just take a sabbatical. But very kindly, when I went to Matt Mason and explained to him at the time, I would like to participate in this project, and at the time it was secret. I couldn't even say what I was working on.
Oh, really?
They may have suspected it, but nobody really knew what I was doing. I was just going to Google, and he was very kind and said, "Okay, what we will do is we will appoint you indefinitely as an adjunct professor. You can continue to advise students. You can co-advise students, you can teach classes, and you can write papers, and you can have your email address, but you can't serve on committees,
Okay.
and we won't pay you."
Oh, okay.
And so I said, okay, I could do that. So I was very fortunate to be able to stay connected to the research and academic community. All my students graduated successfully, and I got to learn so much. I thought I knew how to write code before I joined Google. And I was on the Stanford ACM programming team. I thought I was a good software engineer, but I really felt like I learned to be a great software engineer by learning from the masters at Google, and also just all the discipline, code reviews and style guides and unit tests and regression tests and cloud-based tools to do system regression testing. I mean, this was something that I didn't know anything about, and it really helped me a lot.
And you learned this mostly by interacting with the people and do code reviews?
So Google did a smart thing, is they invited domain experts, and I was responsible for doing planning on the Google car. So I had that domain expertise, but they also mixed in with our team really long experienced Google software engineers who were excellent coders, and they taught us how to do the tools for development, where you have code reviews and you have system and unit regression tests and style guides, and I just learned so much from being able to not only have my own code reviewed, but all of us would get copied when changes were proposed to code that we wrote or that our team was working on. So I would see every day, dozens of changes that are being proposed to our code base. And you could just click, and it was all web-based, and I could read what some of the reviewers were saying. And I could also look at the code myself, and if I had any thought, I could just comment. And so it was a wonderful collaborative way to build a working code base together. And scale. And Google, I believe, still has the world's largest single repository.
And there are also some other tools which you can employ to get better at code and learn from more experienced coders, for example, like pair programming.
Yeah.
Are there other tools like that which have been employed?
I mean, one thing that was also amazing was, Google being a search company, was they had a code search tool that at the time was quite unique. It allowed you to basically search for functions, search for things, or search for language features, and you would instantly get results. And you could see the code, you could click on the code, and it would even tell you who modified it last, and even who wrote that line.
Yeah.
And you could see the history of it. And so I would see a piece of code, and before I wrote a function, I would go to code search and I would say, does somebody already write this function? Like, okay, I need a unit quaternion. Right? And lo and behold, there's a unit quaternion class already. And so instead of reinventing the wheel and spending my time duplicating, I would build a library and utilize code in a more modular way. And I thought that was really powerful. And then it also meant that, Google's code was getting improved and bugs were getting fixed all the time, which I really thought was amazing.
And so let's talk a little bit about code. So what kind of code environment are you using? Something like Vim or Emacs or...
I was a hardcore VI user. I started using Emacs, I think, as part of a class, and actually even when we were taking Lisp. Okay. I actually took Lisp from John McCarthy. So he actually taught AI to me, which was an honor. But then I realized it was so much fun to be able to customize Emacs, and I could basically program Emacs to do what I wanted. I could create shortcuts and do key bindings, and so I still am to this day. Like I am so much more efficient writing code with Emacs than any other tool.
So you think Emacs is better than VI?
I came to appreciate the customizability of Emacs. The fact that my .emacs file, now I've worked on it for 30 years, it contains all of these shortcuts and keyboard shortcuts that I've memorized so that I can instantly, get a lot of things done. And I'm much more efficient now writing code with Emacs than I was with VI.
Sounds good. And so let's get back a little bit to self-driving. So what is, in your opinion, how far are we away from really having a full self-driving car? So what is the timeline here?
So I think when a lot of people think about self-driving, it's very important to specify the domain, the operational domain that you're talking about. And, we've now defined these SAE levels, right? Level 5, so level 1 being cruise control. Level 2, now you can have, steering and cruise control. And then level 3, you start to get, okay, now you can take your eyes off the road and it's driving, but you still have to pay attention and be awake. Level 4 meaning you now have a situation where it can do all the driving tasks for you safely, but under limited domain. That means good weather, low traffic, a good map. And that's what we have today. So if you constrain the domain enough, we have self-driving cars, right? Like I could have a road that's a dedicated lane, and it's got a map, and it's good weather, and it's during the daytime, and there's no pedestrians. Yeah, we can deploy that today. But what people really think about is level 5, which is a car that could drive anywhere a human could, in any weather, in any traffic condition, anywhere in the world without a map. And nobody's even close. I'll just put it that way. Like we're still far away from that level. However, I do think there's a lot of applications that are here today, like Waymo now, giving 100,000 rides. I mean, I'm very proud to have been part of the genesis of that team. I don't know if they're still running my code, but I do think that the potential's there. Of course, they may not be able to deploy in snowy parts of the world, right? But they can deploy in places with good weather and actually pretty hard and complicated traffic. So I see it eventually getting better and better and better. And so
who do you think is like furthest ahead from all the companies like Waymo, Cruise, Tesla? Who do you think, Toyota of course, who do you think has actually the advantage right now?
It depends on how you divide up the technology. I do think, for robotaxis, Waymo's a clear leader. For sure. They've been at it the longest, and I know, just because I know a lot of the people, that they have really great talent and they have the right tools and the right approach. But I'm biased. So because having been part of the team and that I may be biased. But if you talk about advanced safety, that's something that I think Toyota, I'm very proud that Toyota is investing strongly in, and we're actually very open. We tend to open a lot of our safety technology because it's the right thing to do. And I think, among many car companies, Toyota is very committed to safety. And so when you think about full self-driving, automated driving, there's different applications. Some people are at it because they're just trying to monetize mobility. It's all the robotaxi business. Mm-hmm. But others are really thinking about mobility for everyone. A couple years ago, I had to take away the car keys from my mom, right? Like as a family, my father and my brothers and sisters, we had to do that. And that's hard. Someone loses independence and freedom. And in fact, all of us eventually are too old to drive. So we will eventually lose that freedom of mobility that comes with having a car. But with an automated driving car, maybe you don't have to. It means that even if you're too old to drive, you still have the freedom of mobility. You can go anywhere you want, anytime you want, safely. And that's something that I think Toyota's very interested in, is how does we use automated driving and self-driving cars to provide mobility for everyone. Maybe people who are wheelchair bound or cannot drive for some other reason. They could be blind. So there's many reasons why somebody couldn't drive. But can we open up the freedom of mobility to all those people? And that's something that I feel like Toyota has a good chance of still, continuing to lead and innovate in that.
Mm-hmm. But to achieve actually like level 5 autonomy with a car, do you think we already have all the tools? It's just like a very, very big technological challenge, or do we still need some new scientific breakthroughs to actually get there? Or
I mean, definitely driving in bad weather. It mostly becomes a perception problem. Mm-hmm. And I remember when I was testing the Google car with my colleague Hy Mervite. He probably remembers better than myself, but we were driving down Highway 1, and I was the safety driver behind the wheel to take over if the system got confused or needed help. And I remember at some point the fog rolled in. Mm-hmm. And it suddenly became really foggy, and the system started, not being able to localize, not being able to perceive objects well. So I disengaged the system, and then I realized that actually I couldn't drive. Like the fog was so dense that it was actually unsafe for me to drive. So we just had to pull over and wait for the fog to clear. And so, if we had better sensors, and actually if looking at the data that the car had even at that time, radar can see perfectly well through fog. LiDAR, you start to get errant returns. Mm-hmm. So, but with good tuning and hyperspectral imaging, I think you can, have higher frequency electromagnetics that pass through fog or lower energy like radar, right? So the higher energy will interact with the fog, but the lower energy passes right through like radar. So I think a truly capable self-driving car will actually be more perceptive than a human, and it doesn't have to obey the perception constraints that humans have. Like all we have is our eyes and our ears and our force feedback of our skin to control a car. But we also have a lot of proprioceptive models. I mean, the prior models of the map of where we're going, and also how traffic behaves. And that, to me, actually, just is the main thing that I think is still missing. What I learned from working on this technology for over 10 years is driving in traffic is a social behavior. The rules of the road help maintain order in what would otherwise be chaos. But the reason why it's social is because at a four-way stop, right, you actually look at the driver and you might wave someone on, or, there's an interaction that happens because you can't read the mind of the other human. That's why we have turn signals. But the beauty of a robot car that's connected is that it could instantly read the mind of every other connected robot car around it, and it could broadcast its intention to every connected car around it. So if we waved a magic wand and we said, okay, now we have no more human-driven cars in the world, and all we have is robot cars, I honestly think we don't even need traffic lights. Like we might, we don't need turn signals. Like the cars would just broadcast their intent, and they would, be polite, and there would be never accidents, theoretically.
Yeah.
But unfortunately, we have to be backwards compatible with the rest of the world. So we're going to have a long time where we're going to have human-driven cars and robot cars driving together in traffic. So the robot cars have to be able to behave in human-driven traffic. And that means they have to understand the social norms of human-driven traffic. And so, as I mentioned in my talk to this conference, one of the most exciting things I feel is data-driven techniques to program behavior. Because people don't drive the same in London or Mumbai or Tokyo or San Francisco. There's different conventions, different rules, different behaviors that are accepted as normal behaviors. And you can't have a robot car that is not behaving like the median driver. So the biggest thing I learned in the last 10 years is that to program a car the safest, it should drive like the median driver. That means not at the extremes. If you're too passive or too shy, it's actually unsafe because people can't predict your behavior. Or if you're too aggressive, right? That's also unsafe. So being at the median means other people in a theory of mind way can predict what you will do in a nominal way. And so if the robot car basically behaves like the median human driver, the behavior of the robot car is predictable by other humans. And therefore it fits their model of traffic and it fits their social understanding of traffic.
I think once we have more and more autonomous cars, I think there will also be a lot of jobs which will have been gone. So we will maybe not have taxi drivers anymore, and there are also so many people connected to the automobile industry. But I also think that maybe in the future we will have like new industries coming up.
Yeah.
Do you think that there is like a bigger potential for new industries coming up, and what could that be?
Well, this also opens up like a whole nother podcast about, robotics' impact on labor. But it's clear to me that in the past there's been a lot of fear of new technology. If you just look at, the Luddites, right, with automated looms or farming. There's been so many people afraid that, one of the big jobs was telephone operators, like switchboard operators. There were millions of people employed as switchboard operators, and those jobs were eliminated once we had kind of telephone network switching automatic as computers. But new jobs came up, right? and better jobs. And so, there's been this thinking in robotics that the main jobs that we will automate are the dull, dirty, dangerous jobs. The most common job in the United States is truck driving. I think there's 5 million people employed as truck drivers. But it's a hard job. And oftentimes it's very difficult, especially long-haul trucking. And a lot of people don't want to do that job. Young people don't, that's for sure. So what will it mean if robots start taking over long-haul trucking, but you still need humans to do, shorter trips or other delivery or other driving tasks? I think, again, it'll be a long time before we have, a truly level 5 car that can drive anywhere a human can. So there'll still be jobs for drivers, I think, for quite a long time. But eventually there'll be choices. And I always used to say, much like riding a horse, people do it as a hobby for fun, but you don't have to do it. Whereas, 150 years ago, if you wanted to get around, you had to learn how to ride a horse. So now I think in the future people can choose to drive a car, and they may enjoy driving a car, and Toyota always thinks it's fun to drive, but you'll have choices, and if you don't want to drive, you don't have to. I always say I like driving, actually, but I don't like commuting. Like commuting is annoying, right?
Yeah.
I felt like it's wasting my time. I should spend my time doing something else instead of being stuck in traffic. But I enjoy the thrill of driving when it's open air on a highway with beautiful scenery, moving fast. It's fun. So I think these are kind of the choices that this will open up. But going back to your question about robot and labor, one of the things that I always felt was interesting was, let's say AI displaces or replaces half the jobs in the world in the next 50 years, which some people were saying could happen. Does that mean that half the world is unemployed and the other half the world is employed? I don't think that should be the case. In fact, what it should be is that the robots that are doing all that work and creating all this value, hopefully it's creating value for the planet, that somehow that value that it's being created should be distributed so that people can have their time back. So instead of having 100% of the people, 50% of the people employed, we can still have 100% employment, except that people only have to work 20 hours a week instead of 40 hours a week. Wouldn't that be nice?
Well, yeah, for sure. But and another benefit would be that we can actually move on to more, other bigger tasks that we could solve. So, talking about this a little bit, so what do you actually think are the most pressing problems right now for society at large?
I mean, I do think that we're going to have to deal with the impact of humans on the planet to have a sustainable future for our children. We have to be responsible. For too long, we have extracted resources and caused pollution and some damage that some of it's, seems even irreparable. But I'm an optimist. I do believe that if technology doesn't change, there might be a reason why people might be pessimistic. But technology is improving. And I feel we have an opportunity and in fact the duty to be optimistic and try. We shouldn't give up. Like the worst thing that can happen is young people feeling like, our planet's being destroyed, I'm just going to give up. That to me is irresponsible. We actually have to try, and we have to put the perseverance, because humans have always surprised us, and technology can change the rules. So I feel optimistic that we'll be able to face these challenges. But I do think actually wealth inequality is another issue, and there is an unfortunate side effect that could happen. If somebody creates a robot that actually produces value and does work in the global economy, should the person who gets the wealth created from the robot be the owner of the robot only? Or is the labor that the robot is doing somehow gets taxed and redistributed to the rest of society? So then we can support and have a safety net and provide fundamental human rights like education, healthcare, societal care. These are things that I think education. These are fundamental rights to all people. And if robots can somehow allow us to do that, so that we could have universal basic income, and we can have people who can work as hard as they want if they choose to, but at least their basic needs can be met. And that would be nice, and maybe we could have, all of us would have a little bit more time to pursue the things we love, our passions, whether it's raising our children, taking care of our aging parents, contributing and volunteering to the community, writing books, playing music. There's many things we can do that bring us joy, and then the robots can actually pick up the slack. That would be nice.
Yeah, that would be nice. And talking about community, so you were also co-founder and CEO of a very interesting project, Woven City by Toyota. So I think it was started in 2018. Can you maybe quickly talk a little bit about what is actually Woven City and how were you involved there?
Yeah, so I'll back up a little bit. So in 2015, I joined Dr. Gil Pratt to found the Toyota Research Institute, which was amazing. partnered with top universities like MIT, Stanford, Michigan, and now we partner with more. But we assembled a group of 300 really good scientists and engineers to build safety technology and automated driving technology that would expand mobility for everyone. And we made a lot of progress in 3 years, but it was clear that if we really wanted to commercialize and launch into a product a lot of this technology, someone had to go to Japan. And so that ended up being me. So I went in 2018 to Japan to form what at that time the company was called Toyota Research Institute Advanced Development. So in the car world, doing advanced development doesn't mean that the development is advanced or sophisticated. It just means it's in advance of mass production. So you take an R&D idea and you develop it so that it's advanced enough so that it could go to mass production. And so we started this company. It was a commitment by Toyota for 5 years and $3 billion to create this company. And I was really grateful to be able to hire some of the best people I knew and really change the way that we were building software. And I'm very proud of what we were able to finally do. We launched the advanced drive product on our Lexus LS and our Mirai, which was the first product for Toyota and Lexus to have deep learning embedded. But in parallel to that, the president, Akio Toyoda, was really thinking about Toyota's role in the society. And is particularly after the Fukushima earthquake in 2011, which was a terrible disaster that a lot of people don't realize. 20,000 people lost their lives in that disaster. But it wasn't just a humanitarian disaster, it was a disaster for the economy, the agriculture. People lost jobs, companies went out of business. So the people in Fukushima who'd suffered all this human loss and tragedy now were losing their jobs and their livelihoods. And so he wanted to do something, and so he made the decision to build a factory in Tohoku and create thousands of jobs, well-paying jobs for people living there. But in order to do that, he had to make the hard decision to close the factory that was in Shizuoka-ken, in Higashi Fuji. And so basically what happened was the city of Susono, where the factory was located in Shizuoka, people were quite sad because some of them had worked there all their lives, and that was creating a lot of value for the community. So instead of just abandoning that land, the president had the idea to turn it into a mobility test course, an innovation, a place where we could have advanced technology tested and deployed in a real city. And that became Woven City, the concept of Woven City. And in 2020, he announced it at CES. And then, of course, the pandemic hit right after that. But I was brought on early to help lead the project, under Akio Toyoda, together with Daisuke Toyoda, his son. We created a team that was responsible for planning, executing. We partnered with amazingly talented people. Bjarke Ingels, the famous Danish architect who runs the Bjarke Ingels group, helped design some of the cities. We partnered with other Nikkei.
So is the city completely rebuilt, or? So
the factory was torn down. We finalized the designs for phase 1 of the city. Now it's a huge area.
And right. It was all built from scratch, basically?
Yes.
Okay.
Yeah, so phase 1, actually, the construction completed just this summer. And now we're testing, and we're hoping to open fully to the public next year.
And how many people are living in Woven City right now?
When it's finally said and done, we feel that the city could accommodate up to 10,000 people. But in the beginning, there'll be several hundred people living there in phase 1 just to test it out. But I've asked Akio Toyoda, what is the vision for this city? And one of the things that he has said is that it should be a living laboratory that's ever evolving and never finished. So it should be continually innovating. So phase 1 will be completed, and we're going to learn from it, and we'll start building phase 2 and start building phase 3. So it's a really exciting project. I'm so grateful to have been involved with getting it off the ground. And now, of course, there's a Woven City management team, which is now leading the project, and we have both the science teams and we have some robotics teams, and I'm really excited about what they will create. But hopefully it will be a center and kind of a unique place in the world where mobility, technology, and innovation happens. Right at the base of Mount Fuji, which is a beautiful, beautiful location in Japan.
Have you ever been on top of Mount Fuji?
I have. Actually, I climbed Mount Fuji for the first time 3 years ago. And it was at a time when the pandemic was, happening. But my son was a Boy Scout in Japan, and they organized a hike. And so we got up, we drove up to the mountain and slept in the car until 5 a.m. and then started hiking at 6. It took 7 hours to climb the summit, and then we looked around the rim, and it took another 5 hours to come back down. But I have to say, I was 50 years old at the time, and going up, I was tired, but I felt healthy. But 5 hours of walking down the hill actually hurt my knees, and my body didn't recover for weeks. But it was a beautiful, beautiful experience, and they have a saying in Japan, a wise man climbs Mount Fuji, a fool climbs Mount Fuji twice.
So let's get back to Woven City a little bit. So there's also something which is called the Inventor Garage there.
Yes.
So how can I actually imagine this? So are there is it like a research institute, like in a smaller scale? And what are actually the concrete projects people are working on there? So I know the main vision is mobility, but what are more concrete projects there?
Well, it's really evolving the concept, and the goal of the Inventor Garage is to create a place where entrepreneurs could try out their ideas. And just to give you an example, Toyota actually has been doing mobility innovation for a long time, like personal mobility devices. I don't know if you heard about things like the winglet, places where you could ride on e-scooters things, but until recently, there was actually no legal framework or precedent to test those because they're prototype projects, and there's risks to test them on public roads, and maybe you need to change the infrastructure in order to have these devices work well. Like, they should be smart, and they should communicate with smart traffic lights or smart crosswalks. So there are many things that are related not just to the device itself, but to the environment. And Woven City is a place where we can actually control and change the environment because it's privately owned. If we need to, change the lanes or, add a smart crosswalk or add a smart street light or something like that to make the environment safer and mobility safer, and you want to test out something, you want to try out a new device as an innovator, an entrepreneur. So we want to invite those inventors to use this unique test course for mobility, but give them infrastructure. So that means you don't have to build your own test course. You can come and collaborate and get ideas, and you can get feedback. So people who are living in Woven City actually opt in to giving feedback to these entrepreneurs and trying out things. That's something that's very hard to do, to do user studies. Like, how do you get feedback from actual customers if it's not legal to sell your invention, right? So you have to basically find a way to prototype and test, and we feel that this Inventor Garage could maybe accelerate innovation by having inventors from all over the world come to this unique place, this beautiful place at the base of Mount Fuji, and try things out.
So could I maybe call this like a very big startup incubator for mobility?
I think so. I mean, that's one of the functions. Obviously, there's other purposes. The other thing we're looking at is how can we promote sustainability. So, our goal is to have, carbon neutral technologies for life, and carbon neutral mobility integrated into our cities, have safety in our cities so that people don't have to worry about car accidents anymore. That to me is a really big motivation. So it's not just the startup incubation, which is a goal. We hope that that's a byproduct of having the city, but we hope that this is a place where we can lead on safe mobility for everyone as a mission.
That sounds pretty good. So let me quickly talk a little bit about success. So I would say you had up until now a very, very successful career. So what is actually your personal definition of success?
I really like, actually, even when I was in college, the quote from, I think it's Pew, E. Pew. He said that, if the meaning of success, if one life has breathed easier because you have lived, you are successful. So I love the concept of not just doing work for yourself, but trying to leave something, a legacy, to the next generation of people, or people around you, giving back to the community. I think, to me, that is something that if we all did, maybe we would have no more wars, and we would have peace, and we'd have prosperity for everyone. So for me, being successful is feeling that I had an impact positively on other people, and that's, I think, the reason why I was attracted so much to teaching. I mean, not only because I was raised by a family of teachers, but I really felt that mentoring young people and helping young people achieve their dreams is something so noble and worth doing, because in my experience, it's such a privilege to work with bright people who are passionate and talented, like places like at Carnegie Mellon, where they take an idea and make it something far greater than you could have ever imagined. So, to me, if I've been successful, it's because I got to work with talented people who magnified my ability to get things done, and I'm so grateful for that. So yeah, if we can all help each other and support each other, and as a community and as a species, make the planet safe and prosperous for our children, that would be success.
That sounds lovely, for sure. So do you actually believe in daily habits to achieve goals? And maybe you could talk a little bit about how your day looks like. Do you have a very strict plan? Do you have very daily habits which you always do every day? So how do you actually achieve success?
Well, I have to say that it's changed. My daily habits have changed a lot.
No more programming, I guess.
I still try to keep sharp on that, actually. I haven't been able to write code as much, especially when TRIED, which eventually became Woven Planet Group and now is Woven by Toyota. It evolved several times, had thousands of employees. I could no longer write code. That happened even before that when I was engineering director at Google, but I would always try to review code. So I would always be checking what code is happening, what's being written, and sometimes I comment. And of course it freaks out an engineer when the CEO comments on their code. But I always felt that if I had some feedback, and also it helps me as a leader to be more hands-on, deep down as to what's happening on the ground, and what is the state of our code, what are some of the issues that the tech team and the engineering team is struggling with. And if I can help, great, but also it's a way for me to honestly stay current and learn, because the language is evolving, the technology is evolving, and I get out of date and my knowledge gets stale. So I'm always trying to just keep studying and keep learning. But my daily habits, when I was younger, I have to confess, at Stanford, I basically pulled an all-nighter every other night. I was not sleeping every other night for a really long time. And looking back, that was a horrible thing to do from a health perspective, mental and physical. But at the time, I really felt that I had this great privilege to study at this university, and I should spend all my time learning as much as I could. So I actually had to get special permission to take more than 20 units a quarter. Nominally, if you take 12 units in a quarter, that's like a full load. But they allow you to take up to 20 units. But I actually petitioned to take more. And the only reason that they let me do that is because I had done well even with a full load of 20 units. And so I took more. So I was taking more classes than I should have. But to me, I was thinking the only thing that matters is how much I learn. And I had this opportunity to take classes from every department from some of the world's best teachers and just learn everything. So I took classes from every department. I took Shakespeare, I took ancient history, I took literature, psychology,
you
business,
indulged yourself
economics,
in knowledge.
Yeah, I mean, and what I did was actually the students at Stanford had at that time, I don't know if they still do, it's probably online now, but they published a guide that was not sanctioned by the university, but it was essentially a student rating of classes and professors. And I would look at that, and I would actually just look at the teachers who were highest rated, because I figured if people and students are saying, I really love this class, it probably meant that the teacher was inspiring them, communicating well, and so I just sought after the top-rated teachers. It didn't matter what they were teaching. So I remember one time I was taking advanced Shakespeare as a computer scientist, and
how was that?
We went around and there were, everyone was like a PhD in literature, and they're like, we were self-introduction, and I said, well, I'm a computer science studying robotics, and they're like, why are you here? Because that was a highly rated class, and I learned a lot, and because I felt I didn't know the literature as well, that professor actually allowed us to get extra credit, 1 point per line that we memorized of Shakespeare. And at the end of that quarter, I had memorized 400 lines of Shakespeare, more than any other student. That was something I could do, like better than the other students, I guess.
Not bad. So do you have any other advice for maybe like early career researchers who want to get into the field of robotics or computer science, apart from like studying very, very hard and maybe taking classes on Shakespeare?
Yeah, I mean, just going back to the daily habits, I don't recommend staying up all night, every other night. I think, take care of your health, get enough sleep, have some work-life balance. But, for what's amazing to me is that we have so many tools and technology now to study, to learn, to do research, to progress the field. It's such an exciting time. What is important now for young people, I feel, is being able to work as a team, being able to communicate well, and to focus. So to deeply study. There's some, in the news, people are saying that young people are, the TikTok generation is too distracted. They can't focus. They don't read books anymore. That's a shame, because one of the things that you have a privilege of doing if you're studying, especially if you're getting a PhD, is you can really focus and deeply, deeply think about a topic. And hopefully at the end of that deep thought, you will extend the boundary of human knowledge. And that's such a great contribution to have. So to me, the other thing I would share is I took one of the last classes that Linus Pauling, who's one of the only 5 people in the world, I believe, who has won 2 Nobel Prizes in 2 different fields, in chemistry and physics. And Linus Pauling, when he taught at Stanford, he said, you should change fields every 7 years. Meaning, 7 years to become an expert in something. But then you don't stagnate. You actually become a novice again. Change fields, but you're bringing with you the expertise you learned in your other fields. So he deeply studied physics, won a Nobel Prize, but he changed to chemistry. But he brought with him, he didn't know anything about chemistry, but then he brought with him all this physics knowledge. And then you look at problems differently when you're an expert in another field. So I think that's wonderful life advice, and I've actually followed it. I was kind of a grad student postdoc for 7 years. I was 7 years at Carnegie Mellon, 7 years at Google. I've now been 8 years at Toyota, so I'm overdue.
So what is the next big project you want to tackle, or the next big subject you want to
I've been thinking a lot about how all of this technology convergence that's happening can bring robots out of the factory. We have so many thousands of robots, assembling things and building things in factories, but now they're starting to move out to semi-structured environments and unstructured environments, whether, I think the step between home robots and factories is warehouses, logistics, robots that can do a lot of, hard, difficult, dirty, dangerous tasks, that need to be done. And we have enough perception now, and our planning technology is getting better, and we have big data, and we have learning and language models. And so I think there's a lot of things to be done in robotics, and I'm excited about trying to maybe do something in that. So who knows, but I'm thinking a lot about it.
That sounds good. So you mentioned also reading books as something, as an advice to researchers.
Yeah.
Is there maybe like one book or something which has really deeply influenced your life and maybe changed like your trajectory even?
Wow, that's hard. I don't know if could pick one book. I'll have to think about it.
Well, you can also pick 3.
Yeah, that's true.
Or a group of books.
I have to confess, when I was a kid, I gravitated a lot towards adventure books, fantasy. I loved Lord of the Rings, the Belgariad, the Sword of Shannara series. I loved those things. But I was very fortunate that my mother was a school teacher for 25 years. She taught elementary school. And growing up in Oregon, it rained quite a bit. And so sometimes on a Saturday, she would just get us all and say, we're going to the library. And you could get a youth library card in Oregon, and it would allow you to check out 12 books at a time. And so I would check out 12 books, and I would read them all, and it was fun. You could just read anything, and there was no internet, right? If you wanted to find something out, you had to actually go to the library. And I just got all kinds of books, and I do remember, I really enjoyed, Foundation series, science fiction, just thinking about how technology might change, how people might explore other planets beyond our own. I think science fiction really became something I very much enjoyed.
So besides the Foundation series, was there like some kind of book in science fiction which also deeply influenced you, or which you really liked?
Hitchhiker's Guide is wonderful. I think there's a lot of different things that I would say that impacted me quite a bit. But I really enjoyed also later in life, reading more biographies of people. So one of the things about reading books is that, and this is something that I heard from my former boss at Google. Kannan Pashputhi was an engineering director at HP before he joined Google, and then he was a director there, and I reported to him. And he encouraged me to never stop reading books. And his reason was, it allows you to accumulate life experience beyond your own. So each of us is a human with one thread of existence through space-time. Right, our life trajectory is this one path. But when you read a book, you could actually jump to other parts of life experience, and you learn from other people's experiences. And in some ways, we were talking about giving robots artificial experience. This is a way to give humans artificial experiences, because you put yourself in the mind of the character making decisions. So whether it's interactive fiction, watching a movie, playing a game, but reading a book gives you a way to expand your life experience beyond your own. And to me, that is the most powerful thing. So I encourage all young people, read. It's an amazing way to develop not only your thinking skills, but also to develop your life.
Is that actually a daily habit for you, reading? Or how much reading can you actually still get?
I set a personal goal to try to read 50 books a year.
Nice.
I have to confess, in the last 10 years, I haven't made that goal, but I'm keeping it ambitious for a reason. I usually read at least 25 books a year. And I was part of a book club for chief digital officers. So a lot of books I've been reading recently have been about management and IT, and how do you help teams transform, things related to my job. But I also like to read for pleasure. And I recently read Arnold Schwarzenegger's book, Be Useful, which was about kind of developing yourself. It's also a great book.
Yeah. And so when is your perfect reading time? Do you like read in the morning or more in the evening?
I've been a night owl for all my life, to be honest. But I have learned that as I got older, it became easier to wake up. And now I don't even have to set an alarm. I usually wake up before the sun now. So I have more time in the morning quietly to read.
Yeah. Okay. That sounds good. So we're almost at the end. I have one more question. So I think, you wrote like 125 papers and you have like 50 patents. So what would you say over all those years? What would be like the greatest contribution from you? What do you think was like the biggest one for you yourself?
I guess it would have to be my collaboration with Steve Laval. RRT-Connect has, been. I was very honored that it was selected as the inaugural, ICRA milestone paper, which, looking back 20 years, it was the most impactful paper within a 5-year period between 1997 and 2001, and to be chosen was a real honor. Again, it's in academia they say it's the silver bullet, that you're lucky if you manage to get one. But I am proud of other papers and all my students who did such amazing work. But I would have to say RRT-Connect is, if I have one lasting contribution, it seems to be something that has made a difference, which I'm so grateful and humbled for.
Yeah, for sure. Well, it was really a pleasure to talk to you.
It was a great pleasure for me too.
Thank you so much.
Thank you.